In this video, I'll discuss about the theory of basic time series analysis. So we will learn what are the different types of uh, you know econometrics models in time series forecasting. So we'll basically learn what are AR, MA, uh, uh, ARMA, ARIMA models. Okay, so before we begin, let me tell you that this is slightly difficult to understand um, because this requires a lot of mathematical rigor. So we will not get into the too much details into the mathematics of it because it will be otherwise it will be a more complicated and a boring subject. But without worrying, because the internal calculations are mostly taken care of by the statistical software and the algorithm available in statistical software. So we'll just understand how to use time series forecasting models like ARMA or ARIMA to do the forecasting. So the focus will be more on application part, and of course we'll touch upon most of the theory part as well. So some of the terminology that we'll be starting with. So before we begin with the terminology, so let me first tell you what time series forecasting is all about. Well, um, you might have already heard about forecasting in other type of econometric models, like regression models and so on. Right? There also you do forecasting. Now, obvious question that comes to your mind, that why another type of forecasting? Why we need to use time series forecasting when we have multivariate forecasting like regression? Right? So what happens in regression? You have a y, then you use some sort of x to forecast y, right? That's the multivariate regression. Now, in number of cases, your x or the independent variables or the covariates or the factors, whatever you call it, are not available all the time. Okay? And even if it's available, many times there are restrictions. You cannot use these variables in order to do the forecasting. All right. Many a times you will come up with scenario where you only have the y values and y values for different time periods, okay, from different time periods, okay, and you do not have any x, or you actually don't know what are the factors or the variables which are related to your y, right? So in such scenario where you only have your single variable or the dependent variable or the variable of interest values are available, you don't have any covariates available, then you go for what is known as the time series forecasting, because you have only one variable in place, right? Time series forecasting. So what you do is that you simply plot the trend of that variable and see what is the pattern in that variable y, right, over time. Okay, so over time you simply see the pattern, and based on the pattern, historical pattern, you simply extrapolate to the future, extrapolate to the future, right? So in normal regression, you used to take the independent variables to do forecasting y, whereas in time series regression, you will use, say, yt equal to yt minus 1 plus some error. Okay. Okay, so this will be one simple form of model. Okay, we call this AR model. We'll talk about it later. So here you do not use an independent variable. You or maybe you can say that you are using it, but you don't use a different independent variable. You use independent variable as the I mean the past value of dependent variable as the independent variable. So here is the variable yt, and then we are using yt minus 1. That you are forecasting the value of y from its past values, right? So previous value of y gives the future value of y, right? And of course the error term. So this is one way of doing time series forecasting. So you only have one variable in place. That's why we call it as univariate time series. because we only use one variable, univariate time series. So in this case, we do not have the concept of dependent variable where y is considered as dependent variable, and then there are so many independent variable x1, x2, and so on. So that is used primarily in multivariate analysis like regression, whereas in time series, univariate time series in particular, you only have one variable in place, and that's what you use for forecasting. Okay, all right. So what is a time series? Well, a time series is a type of series of data or series set of observations on a particular value, okay, and which is taken at different time frame. And one of the best example is stock price, right? Stock price for last 30 days, right? So you have stock price of the same stock for different time periods, right? So that's one example of time series data. So such data may be collected at regular time intervals. Now this is important. Regular time interval. That means the interval between the time periods, we have given t1, t2, and so on. The interval, that means t2 minus t1, which is the interval, should be exactly same. T2 minus t1 should be exactly same as t3 minus t2. The interval should be exactly same. That means either it should be monthly, weekly, or quarterly, or annually, right? The interval should be same. It should be 1 year, 1 month, 3 months, 1 week, daily basis, 24 hours. But it has to be same. You cannot have a difference of 1 day and then difference of 3 day. That's not time series data. Okay. So time series data can be used, and it is actually used a lot in statistic, econometrics, mathematical finance, for different types of applications. For example, weather forecasting, whether there will be earthquake by geologists, and financial forecasting like laws, financial laws, and so on. So these are some of the things which are also useful. Time series analysis is very useful in these areas. So univariate time series is something that I've already told you. So univariate time series are type of series where you only have a single observations, which is recorded over a regular time intervals, right? Like we said, stock price, right? Stock price. So stock price in period 1, stock price in period 2, period 3, and up to period n, where there are n periods. And you do not have any other variable, only stock price or only stock returns, one of these variable. Okay, you don't have any other variable. All right, when you're talking about time series, let's do a brief recap of what is a cross-section data. So cross-section data is a data where you use number of variables at one time point, right? Remember, we're talking about a number of variables at one time point. In time series, we had one variable at number of time points. It's exactly the reverse. One time point and different variables, right? So, say for example, you're talking about an individual firm, right? Or a firm, a company, right? So you're talking about uh, what happens. What happens to this firm in 2011, right? So that's the area of study. So you collected the number of employee, the revenue, the total profit of the company. So these are like the variables, right? And you collect all these things for one time period, that is 2011, right? This is called the cross section data. Multiple variables, one time period. Whereas in time series, you have one variable and multiple time period. If you take only profit in 2011, profit in 2012, profit in 2013, then you call this as time series data. So this is how time series data is different from cross-section data. So we use the multivariate statistics or regression in cross-sectional data, whereas in time series data you will use the univariate time series modeling. All right. So what are the pattern that you can find in time series data? So depending on the frequency of the data, so which could be hourly, daily, weekly, monthly, quarterly, you can actually find different type of pattern in the data, and you can actually use that pattern to do the forecasting. So sometime your time series data could look like this, sometime it could look like this, okay, sometime it could be straight line, sometime very random, something like that, completely random. So this is totally constant, we cannot do anything about it. This is very cyclical, that means there's a clear pattern, but it's very predictable. You actually don't need a sophisticated time series model for all these things. This is very predictable series. This is like a sine x series, right? Trigonometric function, whereas this is somewhat difficult to predict. So probably this is one series where you need time series model. And this one, which is completely random, when the series is completely random, you cannot actually predict anything. I mean, you cannot predict anything, right? And when it is totally straight line, it's the values are not changing, there's no point using a model. You can actually simply do a guess, and it will be perfectly okay. You do not need a model for all these things when it's a straight line. So you probably have a downward sloping time series data. We are using the GDP data for one of the state in India. Okay, so this is a downward sloping from 1961 to 2001. So you can say downward sloping data for GDP, and there will be an upward sloping data. So this is the typical example of an upward sloping data, where the slope is upward, right? Upward trending, right? It's increasing over time, right? Sometime you will have upward trending and then downward sloping. So could be mix of both upward sloping and downward sloping. That could also be there, right? So this is a typical case where initially there was a downward slope and then there is an upward slope, right? So this could also be one of the so these are different scenarios or different types of time series that you probably will come across in real time scenarios. So there are different components to time series data. Okay, so there are different components, and it can be broadly classified into trend, seasonal, cyclical, and the random components. So what is a trend? Um, so this is one particular thing that it I mean, if you these words are simply the English meaning or the meaning of the English word. I mean, the technical meaning is also pretty much similar to the meaning in English, right? So when we say trend, what comes to our mind is that either it's upward trend or it's downward trend. So if you use the definition, it's just a long-term pattern, right? It's just a long-term pattern in the data. Either it's upward, downward, or a mix of both upward, downward. So that's, we call it as trend. And then we call it seasonal. Seasonal pattern is nothing but something that appears in regular interval, wherein the frequency of the occurrences is within a year or even shorter. For example, quarterly GDPs or maybe sales. So seasonal could be if you use sales data. So every December, right? Every December there is a peak, because December is the holiday season, right? So you will see that sales data for most consumer companies or e-commerce companies in the month of festivals is actually at a very high level, or there is a peak at this month. So we call that seasonal data. That means it happens only in a particular season, and it should repeat within a year or less. Within a year or less. right? If it is happening over more than 2 years, 1 year, it's not. I mean, by definition, it's not seasonal, right? We'll see what that case mean. So next one is cyclical, right? This is also a repeated pattern, but this could go beyond 1 year, right? So this is one where the pattern could be more than 1 year. So typical examples could be the budget, right? Well, budget need not be just 1 year budget, right? It depends on the country, and when exactly is the budget happening, right? The budget doesn't happen on a particular month of a year in every country. It could actually change. There could be a random budget as well, based on uh, if the government really changes within a year. So there is no particular time period, but you can see that because of some economics scenario, or inflation or recession, something like that, or some monetary policy, you see some sort of repeated pattern that is happening, right? Some sort of wave like pattern, right? And two important points: the cycles are not regular. That means you don't see it at a very regular interval of time. That could be up here and then long time, and then up here and then suddenly another up a long time, and then there's no regularity as such. And it also deals with it's also related to cases where it happens with a number of other cases, like economic recession, inflation, you know some monetary policy changes in the country, and so on. So some factor really affects this. So it's not just because of some you know the time factor, like festivals or something. Festivals are uh, already pre-decided, right? But budgets are not. Budget could happen, or budget decision of coming up a new budget is actually random, right? Government decides when it's going to come up with a budget. So that's cyclical. And the last pattern is the random, and this is the easiest to understand. So random is like anything that cannot have a particular pattern, right? It's totally random, as it as the word says. You do not have any pattern. You cannot extract any pattern out of it. So it's totally random. So the idea behind univariate time series is that to use the past values of the series data to forecast future, right? So what are the variables of interest? It could be stock price, it could be GDP, it could be sales, and so on. You can use it for variety of purposes. Whether you are working in a company, you are working in a bank, anywhere where you have time series data available, you can use this. And it's slightly difficult to understand. Theory is slightly difficult to understand, but when you apply it, it's not that difficult. So some of the important uses of time series forecasting is forecasting inflation. So most central banks used ARIMA forecasting, or time series forecasting, for forecasting inflation rate, unemployment rate, and so on, or even exchange rate, and so on. Uh, and then companies also use for sales forecasting. Finance company could use for interest rate forecasting, and so on. Okay, some terminology before we go into the modeling. Okay, so when we call a series as white noise, okay, so when we say series, it's just a series of numbers. Okay, so series is nothing but a series of numbers. A stock price of Tata Motors. Okay, stock price of Tata Motors, say it is 100 rupees in day 1, 120 rupees in day 2, 125 day 3, 119 day 4. So this is known as a series. Okay, so where it says it's a series of numbers with a fixed interval, right? So when we call a series as white noise, so this is the definition. A series is called white noise if it is purely random in nature. So let epsilon t denote such a time series where it has zero mean and has a constant variance. So zero mean, that means it is like this. It is 50% up positive, 50% negative. So when you sum it, it actually zero. So if you take the expectation of the this term epsilon t, it's actually zero. So in white noise, the mean is zero and the variance is constant. Mean is zero and variance is constant, right? Or we can also say mean is also constant. That's also one form of white noise. Sorry, in white noise mean has to be zero. Sorry. So in white noise mean should be zero and uh, variance should be constant. So in this case, the scatter plot, if you do a scatter plot of that, you will won't find any pattern in the data. Hence, if a data shows a time series shows time series data shows white noise features, so it's considered as a white noise, then you should stop doing time series analysis. Okay, you should stop. There is no point. There is no point doing time series forecasting, because this is one series which cannot be used for forecasting. It's such a random thing. Random series cannot be used for forecasting, right? That's why white noise series cannot be used for forecasting. So you should stop there, right? One of the way to do forecasting white noise is simply take the average. Simply take the average, and that's the best forecast. That's the best forecast available for this series. So simply take the average of the series, and that's the best forecast you can give for the next period. So if series is not white noise, then you can go for time series modeling. And then what are the models available? So we'll start with autoregressive models. Autoregressive models are the models where the forecasting is done based on the past values. So if yt is one is the current value, yt minus 1, yt minus 2, yt minus 3, these are past values. So yt is a function of the different past values, yt minus 1, 2, 2, yt minus 3, and so on, and the error term. But now question is how many past value to use, right? That's the main important thing. How many past value? That means will you take only yt minus 1? Will you also take yt minus 2? Well, we'll see how we determine that, right? The common representation or the model which is represented normally, and we call it the autoregressive model. Autoregressive or the AR model is always with a parameter, right? So when we say ARP model, that means there are p parameters, right? P number of parameters. If you have only this one, all these things are zero, then this is a AR0 model. Okay, AR0 model is yt is equal to beta naught, no y, right? If you have only yt minus 1, then this is a AR1 model. AR1 model. If it is AR2, then up to this much, right? Yt minus 1, yt minus 2. If it is AR3, then include this one also. If it's AR4, go next, and so on. Most of the times you will stop at AR3 and 4. You won't go beyond that, right? Because it will be like, I mean, intuitively you see today's stock price is related to yesterday's stock price and day before yesterday. But before that, it's a long time. That's a long gap. So we don't take after few series, and we'll see how to determine this actual p value. What is the best p value for forecasting, right? So how many number of past values you need to take, that we'll see. Next type of models are known as the moving average model. The moving average models are the one where you forecast by taking the error terms. So if you do a regression of yt with yt minus 1, right, with say beta 1 plus beta naught, you will get error 1, right? You'll get an error 1. Similarly, if you do yt minus 1 with yt minus 2 plus beta naught dash, you will get error term 2. So in every regression, if you regress uh, the series with its immediate past series, then you will get a error term, right? Epsilon 1, epsilon 2, up to epsilon n, right? Now, instead of using past value, you can actually use this error term for forecasting. Right? This was one of the proposal, that instead of using the past values like white in the AR case, in the moving average case, you use only the error terms for forecasting, right? The representation is same, just that we have replaced the error terms uh, with the so we have replaced the past values of y with the error terms. So we do not have yt minus 1 anymore. Instead, we are using the et and then et minus 1 and so on. And remember that these ETs are assumed to be white noise. That means if you take the mean of epsilon t, it should be 0, and if you take the variance of epsilon t, it should be a constant. So it is 1, or it is a constant value. It doesn't change over time. The next type of models are nothing but they are known as the ARMA models, right? So they have both AR as well as MA representation. That means you use the past values and also the error terms. Okay? So in the representation, you will see you have yt minus 1, yt minus 2, yt minus 3. So you have the past values pretty much like your AR terms. So ARMA, this is called ARMA, right? Autoregressive moving average. That means you have AR term as well as MA terms. So you have past values yt, yt minus 1, yt minus 2, and so on. And then the error terms also, epsilon t minus 1, epsilon t minus 2. So it's a combination of both AR plus MA is equal to ARMA. And people have said that this is more accurate many times uh, over AR or MA process. All right. Now we introduce you to a very important terminology known as stationarity of time series model. So time series is said to be stationary if the marginal distribution of y at any time period is same at other points. Slightly difficult to understand, so I'll make it a little easy for you. Then instead of understanding from marginal distribution, and then you'll try to ask yourself what marginal distribution means. So stationarity means that um, uh, the series values are not correlated in some sense. That means um, okay, let me put it this way. The series has constant mean variance. So the basic statistic like mean, variance, all these things are time invariant. Time invariant. That means they do not change over time. So if you take a series, right, and you take such a mean in this period, and then you take a mean in that next period, you take in another period with the same interval, the mean should be same, and also the variance should be same. Although in reality many times it's not the case. Mean will differ and variance will also differ. So stationarity is one of the important criteria in time series modeling. So all the model that we have seen, AR model, MA model, ARMA, the requisite condition is that the series should be stationary. Otherwise, we cannot use this model. So many times your series will not be stationary. In that case, you have to make it as stationary. So in that case, you will be using differentiating methods, or you will differentiate or take the first difference or second difference of the time series to make it stationary. So that's so we'll not get into that, but I'll tell you why differentiating is important in the next couple of slides. So there are some more definitions. There is something known as weakly stationary, covariant stationary, and so on. And some strictly, what we have learned so far is strictly stationary. So in weakly stationary terms, um, the mean is constant, right? The variance is all constant. And if you take a covariance for different two series, it only depends on the difference in the time. That means t1, say t5, right? So if you subtract that, 5 minus 1, that is 4. That means the covariance of the series depends only on the lag k, but do not depend on time explicitly. It is called covariance stationary. So some definitions. As I've already said, a series which is non-stationary can be made stationary after differentiating. And we will not get into the details of it. But when we mean by differentiating is nothing but taking the suppose this is something like that. Okay, you take the first derivative or take the second derivative and then you make it stationary. That is the procedure of doing that. And that's why in ARIMA model, you might have heard about ARIMA. ARIMA, right? The I term stands for integrated, right? So ARIMA is the third. We talked about AR, MA, ARMA. So ARIMA is another type of model where I terms is there. I terms means integrated. That means differentiating. If we're differentiating once, we're calling it as integrated 1 series. If you're differentiating twice, then integrated 2 series, and so on. So I0, I1, I2. If you are not doing any differentiating, it's already at a stationary, then it's I0 process. If it is differentiating once, then it's I1, else it's I2, and so on. So from this slide, the takeaway point is that if a series is non-stationary, you have to first make it stationary before doing the forecasting. And how you make it stationary? By differentiating. So when a series is differentiated, what we call it? We call it as integrated. And what is the order? If you differentiate once, then it's a I1 process. If you differentiate twice, then it's I2 process. Okay? So these are some of the definitions. Okay, so why the series has to be stationary, right? So I'll not cover this topic. I think there are some very fine bullet points. You can read it up on this slide. So stationarity is very important from theoretical point of view. Okay, theoretical point of view. So if you try to do the estimation of time series models, estimation of time series model like AR, MA, ARMA or ARIMA model, stationarity is one of the basic assumption. If stationarity assumption is not met, then estimation is erroneous or the forecasting is not reliable. So that's for theoretical point of view, checking stationarity in a series is very important. The estimation and forecasting of univariate time series is carried out using a very famous methodology known as Box-Jenkins methodology. So these are two statisticians or econometricians who formulated this strategy of doing forecasting. So Box-Jenkins methodology of doing forecasting is an important step or important methodology of doing time series forecasting. It involves three steps: identification, estimation, and then diagnostic checking. And remember, the Box-Jenkins methodology is applicable only to stationary time series. So the first thing that you need to see uh, in a time series whether the series is stationary. So the moment you have the modeling in place, I mean you want to do the modeling, first you see if it white noise. If it white noise, don't do anything. Okay, you cannot do any forecasting, don't do anything. Then check if it is stationary, right? If it is stationary, then start with modeling. If it is non-stationary, first do differentiating and make it stationary. Make stationary, right? And then you apply your time series model like AR, MA, ARIMA, whatever. Right? That's the way. All right. So next terminology is what is known as a autocorrelation function. So autocorrelation, as the name suggests, it correlation with itself. That's why we call as autocorrelation. That means correlation with itself. If yt is correlated with yt minus 1 because both are series and you can actually take a correlation, then it's autocorrelation because the same series is being taken used for calculating the correlation with the same past values of the same series, right? So it's autocorrelation. That means correlation with the same series. And why do we need to measure this? This will help us determining the p values or the parameters, number of lags. You remember I was talking about the number of lags to be used in the time series model. So we'll compute autocorrelation ACF function while doing the time series modeling. So we'll compute the autocorrelation value with this formula, which is covariance of yt, and then suppose we want to find out the correlation between yt and then yt minus p, right? Let's say t is equal to 5 and p is equal to 1. So what is yt then? Y5. What is yt t minus p? It is y4, right? So we'll now try to find out the correlation between y5 and y4, right? So that's just a representation. So how do you find it? Covariance of yt minus p. Just put the value of t and p. That I can t is equal to 5, p is equal to 1, and you can have any values there. And it's just a correlation formula. Square root of var of yt is a square root of var of yt minus p. So you have this value and then you find out the autocorrelation values, okay, or the correlation. Autocorrelation, nothing but some sort of correlation, just that we call it autocorrelation because it is the correlation is taken with the same series. Normally correlation is always taken with two different variables, right? But it's only one variable, that's why we are calling autocorrelation. Another important thing is the partial autocorrelation. This is also some sort of a correlation, but it's slightly a variation of that. So partial autocorrelation, or known as the PACF, are used to measure the degree of association between yt and yt minus p, right? So all the time you remove the different lags between them, right? Say this is y5 and this is y1. So I remove y4, y3, y2, and then do these partial autocorrelations, right? So in that case, we call it as a PACF. So PACF is some kind of ACF, just that we remove the intermediate series between this intermediate lags. So there is no effect of y4, y3, and y3 in this case. We only see the effect of y1 on y5 without taking into consideration y4, y3, and y2. So why do we need to calculate ACF and PACF? Well, we need to calculate ACF and PACF just to see to what extent the current values of a series are related to past values. So the idea why we do all this thing, I mean, from common sense point of view, if you are forecasting a series, right, you are taking that okay, today's values are related to past values, but how many past values? Will the next past value, next of next past value, and next of that? How do you know how many past values related to? I mean, logically, if you think today's value is always related to yesterday's values, maybe day before yesterday's, therefore, maybe a couple of days. But after that, that should, I mean, ideally, there should not be any relation, right? Like stock price. Stock price of today is related to stock price of yesterday, day before yesterday, maybe 2 days, 3 days. But beyond that, there will be very less correlation. That so ACF and PACF will tell us that to how many lags or how many periods you should consider for forecasting. So there you will be able to find out the lags. Lags means whether it should take t minus 1, t minus 2, t minus 3 or so on. So how many lags you should take. These are lags. Okay. So so what we do is to know that we plot what is known as a correlogram. Correlogram nothing but the plots of the ACF function with respect to the lags. So by looking at the ACF and PACF with respect to the lags, we select the P and Q value in ARMA, P value in AIR, Q value in MA, right? In ARMA we have two parameters, both MA and AR parameters, P and Q. So the general characteristics, or theoretically, what you can see is that if you are doing a ARP model, the ACF will be, there will be a spike and then it decays. The PFCF will spike and then cutoff will be towards 0. In the MA case, the spike cutoff to 0, and then PACF spike, it decays slowly to 0. In ARMA PQ, we will have spikes decays to 0 and spikes decays to 0 also. So these are some of the pattern, okay, normal pattern or standard pattern of different time series models uh, of pattern of ACF and PACF, and that's how you will get to know that whether you will use AR model, MA model, or ARMA model, right? So you might wonder, right, why we have three types of time series model. Well, we have three type of time series model for three types of different scenarios or different pattern. So how do we know which one is best? By looking at the ACF and PACF, right? So if you're doing a detailed analysis, nowadays it's not required, because nowadays softwares actually give us automatically, but if you do it on your own, you'll be more sure about it. So you can actually plot the correlogram, ACF with respect to lags and PACF with respect to lag, and see which one of them is true. If this is true, then use ARP. If this is true, then use MA. If these 2 points are true, then use ARMA. As I've already said, the first step in the modeling process to check the stationarity, and then do the estimation, and third, do the diagnostic checks, right? So three steps are very clear, I'm sure, because this is standard steps in most econometric models, where you start with diagnosis, whether which model is to be used, if the data series is perfect for time series or not, and so on, right? Then you do the estimation, and third, once you've done the estimation, do the diagnostic checks, just to be sure that your model is actually good enough for practical use. So there are different type of estimations that are available. You can use the Ewell-Walker procedure for estimation, and then there are methods of moment, and then there is maximum likelihood method. So we'll not get into details of what these estimation methods are, but no matter what estimation you use, you never have to use because software themselves use it. You can specify though that which method is to be used, but there will be slight variation of that. You won't have a lot of variations. You no need to be worried about that. These are internal calculations what the software does for estimation, right? Maximum likelihood is the one which we all are familiar with. So because this is also one estimation method used in time series model, so we can use the same thing. But once it's we have already built it, we'll do the diagnostic checking. So what we'll do, we'll take look at a lot of this diagnostics or the statistics from the model, and we'll be sure about it only after be very sure only after we see that these values are at a comfortable range or acceptable range. Pretty much like you see R square, AIC, BIC in regression, right? You don't have R square here, but you have AIC, BIC, SBIC. So the model with the lowest value of above criteria is the best model. So what many a times the software does is that it randomly picks a number of models and will tell you which model suits your model best based on the AIC or BIC criteria. So just me tell you and give an example. So you will be worried whether I want to AR not model, AR1 model. So you are sure that you are using AR model based on the criteria we discussed in the last slide, right? Now you will be confused whether I should use this one, or AR one 2 model, or AR3 model, and so on. So what you can do, if you're not very sure, if you lack sound theoretical knowledge, you can simply fit all these models, okay, all these models, and take the one which is having the least AIC value or the least BIC value. That's the best fit for your model, right? So that's the way you need to do. And finally, for diagnostic purpose, you should ensure that you plot the residual SEF, the SEF of the residual, right? And it should be random, right? It should be random. That means the mean should be 0, and there should not be any pattern in your error, right? It's pretty similar to what you see also in regression, right? There should not be pattern in your error term, right? So diagnostic check is same what you should do in regression. It means you should ensure that the residuals are white noise. That means mean is 0, and that means there is no pattern in your residuals, right? So you can do that post the model estimation, and then you can use, once you are sure your diagnostic checks are fine, you can use your model for forecasting future. So these are the steps. We'll see an example, and probably will be better off. So here is a case study, and we'll do in R. So I have not given the plots here. You can use this codes, and data set is given. You can try it out on your own, and and see, and you can play around with different type of model and see the pattern and so on, right? So there are two case studies. So let's look at the first one. So in this case I'll be using the ARIMA. So I'll use the AR, then I, and then MA. So when we combine, we call it ARIMA. AR means autoregressive, I means you are differentiating. It's a non-stationary series and we are differentiating. That's why it's I, integrated. And then we have moving average because this is MA. So autoregressive integrated moving average. Autoregressive integrated moving average. That means we are using past terms. We are also differentiating. We are also taking the error terms. So we are taking all three conditions and we calling it as ARIMA model. So we'll see how you build an ARIMA model. So this is a data set with death age of 200 individuals. So this is sort of a time series model. And then how do do it? Okay, first take it inside, do the plots, okay, and see if there is a pattern and all. Do some basic checks, okay. uh, and then plot your ACF and PACF and see whether you should use AR, AMA, ARMA, or ARIMA, and so on. Or maybe you can build all models and see which one is the best or which one is giving your best results and so on. Not a big deal. If you have time, you can do that. Right. So you need to install package forecast in R and use the function auto.arima and use your series, and it will provide you the best fit. So when you do that, our data set says that the ARIMA 000 ARIMA 000 is the best fit, right? So it internally computes everything. We do not need to do anything. Internally computes, do the comparison. It has done the comparison and it gives us that this is the best fit. That means the P lag is 0, the Q is 0, and also the I is 0, right? And it only has intercept. It do not have slope coefficient because there is no AR component, integrated component, or MA components. So slope coefficients are all zeros, right? And you also have the AIC and BIC. You can try out other models like ARIMA 001, ARIMA 100, ARIMA 111, ARIMA 101, and you try out all these things and look at the AIC values or BIC values, right? You will see that they're like more than this. So this is the best fit. It's automatically giving us. We can also try manually by looking at all these different forms. So you can check all these models on your own and come up with. So these values you can check on your own using the same package, and then you will see that ARIMA 000 is giving you the best result. And then you can do the diagnostic plot. So what do we do? You simply plot your standardized residuals, and it should be white noise. What do you mean by white noise? That means it should be random. There should not be pattern in your error terms. Once you are sure about it, I mean the error doesn't have any pattern, then you can use this for forecasting. So how do you do forecast? Simply use forecast.arima and then just tell that for how many periods you want forecast. So you want forecast for next 10 periods, right? So this is the syntax. You use this and then you will get forecast for next 10 periods. So that's the way you do time series forecast, ARIMA forecast in particular. There's some more codes you can use for your purpose, and we'll also see another case study in the next video. Hi, in this video I'm going to talk about the panel data analysis. Alright, so as part of this session I'm going to cover the following topics. I'll talk about the panel data, what is panel data, and then I'll talk about how to analyze panel data, and then I'll talk about the estimation techniques used in panel data analysis. I'll then talk about the LM test, Hausman test. We'll get into the details of these tests. So I'll explain the concepts by taking a case study, and then finally I'll conclude about the analysis. So let's get started. So let's first understand what is panel data. You might have heard about time series data and cross-section data. So let me give examples of time series data and cross-section data. The time series data looks like this. You have got the stock price of a particular stock over a period of time, continuous period of time. So you have got stock price for 1st December, for 2nd December, 3rd December, and 4th of December. So you have stock price data for 4 consecutive days. That's time series because it has data for different time periods. And the difference between the consecutive time period is constant because it is only 1 day difference data, right? So this is called time series data. So what is cross section data? In cross section data, you won't have the time component. So here is an example. We have got data for different cities in United States for a particular year. Let's say the year is 2014. So for 2014, we have got data for 3 cities: Florida, California, and New York. We have got the population in millions, average income, percentage educated, and then the rainfall. Okay, so I've got data for different cities for a single time period. That's important. Single time period. Okay, so in cross section data, you will have data for different cross sections only for a one time period. Okay, whereas in time series, you have only one kind of data. For instance, here we have the stock price, but for different time periods. So that's the difference between time series and cross section data. Now, what is panel data? Well, panel data is just some kind of a combination. The way if you combine time series aspect and the cross section aspect of data, then we get a panel data. So let's take an example to understand. So here is an example. So remember in the last slide we talked about a data set which has got information about different cities in United States. So we've got data for Florida, California, and New York. So we've got data for population, average income, percentage educated, rainfall, and we have got another column here which is time. Remember in the previous slide we talked about the cross section data which has got data for only 2014, but here we have got the same data for 2015 as well. Now here we have data for 2 years. Okay, 2 years, or in general we have got data for multiple years, okay, or more than 1 year. So in that case we call this as a panel data because we have got cross section data for multiple years. Now this is our cross section data. So this is the data that we had in the previous slide. So this is the cross section and this gets repeated for 2015 as well, and you can extend to 2016 and so on. You can also go to 2013, 12, 11 and 10, and that is panel data for the 3 different cities. Now what is the main feature of panel data? Well, the main feature of panel data is that it has got cross section component and it has also got time series component. The same cross section gets repeated over time. Okay, the values will of course change, but the same cross section. So we have got three cities, right? So we have got data for the same 3 cities for the next year as well. So it combines both cross section and time series, is known as panel data. So we learned about analyzing such data and how it is different from cross section. Why can't we use the cross section techniques used for cross section data analysis in panel data analysis in detail? So please be with us. Okay, let's move on. Panel data can be categorized into 2 types. One is balanced panel data and the other one is unbalanced panel data. So what is a balanced panel data? If you look at the right hand side of the data set, so this one. So this is the one that we have taken from the previous slide. Okay, so this is called balanced panel. Why? Because we have got data for the 3 cross sections and then we have got data for exactly the 3 cross sections without missing out on any one of them. But what if we miss out on just at least one of them? In that becomes unbalanced panel data. If you look at the left hand side of the data, you see that we have got data for Florida, California, but the data for New York is missing. Whereas we have got the data for New York for 2015, but for 2014, the data for New York is missing. So this is called unbalanced, where you have different cross section. It's not the same set of cross sections which are getting repeated for the next year. It is a different set of cross section which is there for the next year. So if any one of these is missing, which often happens in panel data analysis, where we could come across cases where we have got missing data, that becomes unbalanced panel data. And the analysis used for balance and unbalanced panel data is different in some sense. In this particular session, we'll talk mostly about the balanced panel data. So what are the important features of panel data which makes it different from the ordinary data or data which is not panel data, for instance of the cross-section data? Well, the panel data allows the control over variables we cannot observe or measure. Okay, and we'll understand this. So what is that we cannot observe? Okay, in great detail. So what happens is that in panel data, if we take the example from the previous slide, we have got population for a particular city, let's say Florida. Okay, so we have got 10 million, and then the next year the population for Florida is 12 million. So not only we are having the data for Florida for a particular year, we are having it for different years. So we know the trend that is there in this particular data. So we have two advantages of having panel data. We have got trend, okay, within the variable, okay, and we have also got variation across variables. Okay, so that is a combination of the features of panel, the features of cross section and time series, and that makes it interesting to analyze. And some of the aspects of research require your data to be time variant, and at the same time having some sort of cross section features as well. Some of the unobserved components which do not get captured in cross section analysis are like the examples like culture and ethical. Okay, now for instance, if you are doing analysis of a population data, if you are doing an analysis of a population data for a particular year, let's say 2014, you wouldn't be able to find out how certain aspect of the population is changing over time. Okay, for instance, the cultural aspect, the ethical aspect. If you do an analysis for 20 years, let's say you're doing an analysis from 85 to 2015, so you're doing analysis for 30 years, a lot of things would have changed about the population. People aren't the same what they used to be 30 years ago. So there are certain aspect of the population that changes over time. Okay, so that can only be captured in a panel data analysis and not in a cross section data analysis, and that's one of the important feature of panel data. It also accounts for the individual heterogeneity. Okay, that means how within the individual things change. For instance, how the population is changing over time for Florida and how it is changing for New York. Okay, so one can compare how Florida is the certain certain feature of the state Florida is changing over time compared to new work. So the comparison is also possible in panel data. How do we analyze panel data? Okay, is it the same that we normally use for cross section? So important thing is that it has got both the features, time series and cross section. So the question here is, can we use the ordinary least square? Can we use the OLS? Okay, and what are the problems that one might face uh, by applying the ordinary least square regression in doing the analysis? Okay, now there is going to be problems. Okay, there are problems using OLS in panel data analysis. Okay, not always though, but there are instances where you will have problems, and one of the main reason why you will have problems is because you will have correlated errors. We'll talk about it, and when there are correlated error terms. Okay, now you might wonder why the errors are correlated in panel data. We'll talk about it. Okay, if they're correlated errors, then this will violate some of the assumption of OLS, and that's something to be taken care very very carefully. Otherwise, there is going to be issue. A typical OLS model looks something like this: yi is equal to the estimates a plus b xi plus error term. Whereas a model form for panel data looks like this: yit. So the extra component or the extra thing here is the time component. So I stands for the cross section, t stands for the time series. Let's go both the components, right? For instance, in our example, I stands for here the cities, New York, Florida, and so on, and time stands for different time period, 2014, 2015, and so on. Okay. Now, in this particular case, you will see that the errors will most likely to be correlated for a particular cross section. If you take the population for Florida over time, over 2014, 2015, 2016, and even before that, you'll most likely find the population to be very correlated among themselves, right? Hence, the error term are also most likely to be correlated, and that is an issue in OLS. Okay, so either that has to be corrected before using OLS, or you can use alternative technique. We'll see how we can deal with this problem and how we can overcome this problem while doing panel data analysis. And yes, so for that we'll take a case. We'll take a simple case. So what we're trying to do here is we're trying to predict, we are trying to rather understand the relationship between the salaries of employees with different covariates or different independent variables. Okay, the independent variables are the experience of the employee, the projects, the number of projects that the employee has taken up in his career, and the education, number of years of education the employee has. Now these are the three covariates, and we have got the logarithm of salary as the dependent variable. So this is the dependent variable, and the independent variables are experience, projects, and education. Okay, so we will have a model like this, right? There will be three estimates, and we have the experience, then projects, and then education. Okay, all right, so the model will look like this. Now question is, why do we take a logarithm of salary instead of salary? Well, in some research people take logarithm of certain variables so as to have a better model and one of the reason they take is to reduce the variance. That's one of the reason, and there are other reasons as well. Okay. Um, so we've taken the logarithm of salary as the dependent variable, and we've got 3 independent variables. So this data is available for different time periods. Okay, and we have got different employees. So for employee ID 1, we have got data for 7 years, right? If you look at this data, employee ID 1, we have got data for time point 1, time point 2, time point 3, 4, 5, 6, and 7. So for 7 consecutive years, we have got the data for the employee. All right. Now, how do we build a model? Okay, remember the model that we are trying to build here. We are trying to have a regression model which explains the relationship between the factors like experience, number of projects, and number of years of education with salary. So what we're trying to know here is the marginal effect, like how experience impact the salary of someone. We're also trying to know the relationship in terms of the sign, whether it has a positive effect or negative effect, and so on. Pretty much similar to the multiple linear regression, just that the structure of the data is different in this case. So how do we fit a regression model to this? We'll use the panel data analysis instead of the least square analysis, and we'll take certain aspect of least square analysis as well, and we'll use R to analyze the data or to fit the model. Okay, in R, you have got the panel data model, PLM. So I'll show you the code. I'll give you the code. You can use the code, and you can run the analysis by yourself. There are different analysis one can try out in this case. Okay, one of the analysis is pooled OLS regression. It's one form of regression, OLS regression, that you can use instead of panel data. Okay, the reason why we are trying OLS regression is to show you the weakness of this technique. Okay, weakness. Also to show you that why this particular technique is not very suitable for this type of data set, right? And that will ensure that we have a strong argument for going in for a panel data analysis. So just to show you how to use a pooled OLS regression. So the estimation happens to ordinary least square, and the analysis is pretty similar to cross section. Now, if you just ignore the time series component and use the cross section, what problem one might face, we'll see here. And what is the form of this particular pooled regression? Well, it assumes uniform error variance, right? So you will have if you have, like, let's say we have got two cross sections, okay, group 1 and group 2. Okay, so the only thing that is uniform in these two groups is the variance of the error. Okay, so the error variance is constant. That is what is assumed. So we will not get into details of it, details of how pooled OLS regression is why it is pooled OLS regression, and how it is different from the OLS regression. You can read more about it, but we'll be using pooled OLS regression in this case. So only thing you need to remember here is that the error variance is uniform across different cross section. Okay, so that is one assumption in pooled OLS regression, and we'll use this in this data. So how do we use this? We use the PLM, and then we have got the dependent and we have got the independent. So we have just coded this. So in independent you have the 3 independent variables, right? We saw in the data set. we have got the data, input data, the same data that I showed you, and in the model you have to put it in put it in the kind of model that you are using. Okay. So we are using pooling in this case. So just provide pooling to this particular statement, and we are saving this in a variable called pool. So this is the syntax. Okay, simple syntax, and if you're familiar with R, you should find it very easy. Okay, so we're just taking a procedure PLM which takes argument which has independent variables, dependent variable, the data, and the type of model that we are trying to, a type of uh, you know panel data models that we are trying to fit here. So we'll see some of the statistics in this particular result. So in the results we have got the intercept and the slope coefficients, the R square and the adjusted R square. Remember, this is OLS, so we'll of course get these these things in the results. So what we can see here is that two of the variables are significant. Okay? Experience is significant because it's less than 0.05. Similarly, education is also significant. Number of projects is not a significant variable in determining the salary of an employee. The R square is 0.35 and the adjusted R square is also pretty much the same. So that's what the result from this particular model. Now, is it good? No, it is not good model because it's a bad fit to the data. Okay, we can actually have a better model. We can actually have a better model with higher R square. Okay, with higher R square, which signifies the model's strength. Okay, R square, the higher it is, the better it is, right? We want always very high R square. We want always it to go up. So it ignores the fact that it is a panel data. It's simply we are fitting a cross-section model to a panel data. So of course we will expect a not so good model, and that's exactly what we're getting here. We're getting only 35% of R square, which is not a very good fit to the data. And this is happening because the error terms are correlated and we are not taking care of that. Okay, so we are losing out a lot of information in this particular type of model. Okay, the next one that we're going to do is the between estimation. So this is the estimation type 2. Okay, the pooled one was 1 and this is 2, the second type. So what it does is it calculates the average of the dependent and the independent variable over time and does the OLS regression of the dependent by taking the independent variables. It's pretty simple. So what it does is we have got time series as well as cross section data, right? When we do the average, if you take the average over time, so you'll only get the cross section, right? What do? You simply take the average over time. You have got 7 period, right? 1 to 7th. So you take the average of education, the average of the number of projects, the average of the third variable as well. Okay, and if you do that, the time series component is gone now. Now you don't have data for all 7 years. You just have data for the average of the 7 years. So we are now have if you do that, we do not have to deal with time series. We just have to deal with the cross section, and that is also going to be an issue. But I'm just showing you an alternative technique, like what are the options that you want. Even if you use between estimation, it is not going to be optimal in nature. It might be a little better than the pooled OLS regression, but may not be the most optimal one. Okay, So so the syntax remains same, except the fact that in the model statement we are using between instead of the pooled that we had used last time. The results are pretty much same, except the fact that the r square has gone up now. R square has 0.4 instead of 0.35 the last time we saw. Now, as I was initially, I was talking to you in the last slide that the r square might go up, but we are not sure if this model is the optimal fit. And it has certainly gone up, but it is definitely not the optimal one. It can go up even higher if we use a right model. Okay, so the between estimation is also not a fit to this data. One thing you need to remember here, probably you have to revisit the theory, and I strongly recommend you to learn the pooled estimation and the combined estimation, ordinary least square, pooled and combined ordinary OLS estimation. You should go through the theory to understand this particular this better, because I'm not able to cover like every single thing in this particular video, because the main purpose of this video is to learn panel data, not the OLS one. So I'm just talking in brief about this estimation, but you can always go through the theory to get a better understanding. So in combined estimation, all we are doing is we just averaging it out over time. Okay, so we have got education. Let's, for example, we have got education, number of education for sorry, education of course will not change. Let's take one data. Okay, let's say experience, right? So experience is changing over time. So this is the experience for the first individual, right? We're just taking the average of that in between estimation. Similarly, the number of projects, we're also taking the average of that. Okay, so when you take the average of that, all these 7 observations, you'll only get a 1 value, right? So the data will not have any time series component, and that's exactly what happens in between estimation. In pool estimation, we don't do that. We still have all the 7 observations, but in between we only have the average of the 7. That's why we have got rid of the time series component. What is the next one? The next one is first difference estimation. In this particular type of estimation, we exploit some feature of the panel data. Okay, so what we do is that we take the first difference of the two equations, for different time periods. If you know, in time series we've got the lags, right? So if xt is known as the data for the current time, xt minus 1 is known as the data for the lag period. Similarly, xt minus 2 is the data for the next lag period, right? So this is how we represent a time series data. If you're familiar with time series, this is pretty easy for you. If you're not, so this is how we represent the time series data. So we've got two types of equations here, two equations rather, yit and yit minus 1. So this is for the lag period. Okay, similarly for the independent variables, we have got xit and xit minus 1. Ci is an individual effect. Okay, individual effect as in the effect that is purely for different individuals. Okay, in this example, we have got the data for the employees, right? We have got data for the employee. Now we have got data for education, then projects, and then what else? The education, projects. What was the last one? Okay, the third variable, right? And apart from the 3 variables, there are other things about a particular employee, that also matters, right? For instance, the IQ level, right? So if you compare two employees with same education, same years of experience, same number of project, you still find a difference in the salary. That could be because of uh, the IQ level of two employees. Okay, so that could be one thing. The the uh, the university or the school that a person attended, that also could matter, right? University also could matter. Then family background, parents income, right? That also could matter uh, for the salary of an employee, right? Somebody who has gone to a better school or a better university, whose parents have been able to spend more money or more time for for a particular employee, uh, then there is a higher likelihood, the likelihood that he would have been able to more successful in his profession would have been higher, right? So given these three variables same, you will still find the difference in the salary for two persons, and these are individual specific things. Okay, individual specific things, or also we call it as the unobserved unobserved variables or unobserved features of the data. Remember in the first slide for panel data, we talked about the unobserved things, and I had told that time that I'll be talking about in detail. So this is exactly what it is. Now we capture that in a variable called CI. I stands for the cross section because that doesn't change over time. Also, that's an assumption here. So we just see that the unobserved thing is very specific for a particular employee. So it could be C1, C2 and C3 for employee number 1, employee number 2 and employee number 3, and they will of course differ among them. Okay, so that component is captured in CI. When you take first difference, what is first difference? You just simply subtract the lag from the original variable. So okay, so if we take yt minus 1, we essentially call it as first difference. Okay, and then we take yt and you can go on, you can take second difference, third difference and so on, but this is first difference, and we do the regression by taking the first difference, and that's why it is called first difference estimation. So essentially what we are doing here is that we are taking so we're taking the first difference here. So in the left hand side we'll of course have something like this, plus you have got beta 1 x1 it, then beta 2 x it minus 1 plus ci minus ci. Remember, the unobserved factor gets cancelled out in this case, and then you have the error term and so on. Now that's interesting. When you take the first difference, you actually get rid of the unobserved impact or the individual specific effect on the dependent variable. And technically we call that as individual heterogeneity. Okay, which essentially means the variation or the effect of unobserved things on dependent variables. We technically call it as individual heterogeneity is eliminated from the model by taking the first difference. When we run this particular type of regression by taking the first difference, by getting rid of the individual effect, syntax remains same except the fact that in the statement model you are just using FD. So what are we getting here? We're just getting one significant variable, okay, and that is projects. Okay, so education and number of years of experience hasn't been significant. Now that's a little strange. Okay, so what about the R square? The R square is extremely low. Okay, now we are getting two strange events. One, that two important variables, education and number of years of experience, are coming out to be insignificant. So that's strange, because you wouldn't expect these variables to be insignificant in such cases. Why? Because these are very important in determining salary. So that's common sense, right? And R score is also pretty less, 0.007. That's like less than 1%. That's totally strange, and this result is unacceptable. So you've seen education got dropped because education doesn't change over time, right? So it's totally got dropped, right? Number of year experience is coming out to be insignificant. So this model is also not so very good. Okay, in fact, not at all good. This is totally giving a very weird results. The next type of model that we'll talk about, and this is the pure panel data model, so to say. Okay, one is the fixed effect model, or we call it as fixed effect panel data model. Okay, popular ones, fixed effect panel data model. So what it does is it treats the unobserved individual heterogeneity. We talked about unobserved individual heterogeneity in the last slide, right? And when denoting is alpha I, so we had denoted as Ci. Let's not confuse with the notations. Same, right? We're just changing the notations. Okay. So it's alpha I in this case. So we'll not confuse with the alpha I, which is the intercept here, right? So let's not confuse with that. We'll keep on using alpha I for the individual heterogeneity. So we assume here is that the unobserved heterogeneity for each employee to be correlated with the explanatory variable or the independent variables. Okay, so that's an assumption. So we say that alpha I is very correlated with xi or xit. Okay, so the correlation between alpha I, which is the individual heterogeneity, is with the independent variables is non-zero. Now this is an assumption. Okay, if this happens, we'll be using fixed effect model. Now the obvious questions is like, how do you know this is there, right? We'll see. How do we know that this is zero or non-zero, and what if it is zero? Okay, we'll see that later. So the estimation involves transformation to remove the unobserved effect, pretty much like the the first difference estimation type. Here also we are going to get rid of the alpha I term, the unobserved effect, before doing the estimation. But there are other things as well. You not get into the details of the theory. You can always get into the details of the theory on your own. Since this is an introduction, I'll show more about the application of these things, and I'll talk briefly about the theory. Of course, this is very complicated theoretical topic which needs to be studied in great detail. I'm just giving you an introduction. So fixed effect transformation will look something like this. The original model is YIT, and then we have got the unobserved effect. Let's ignore the intercept for the moment, and then we have got the slope coefficient beta, and then we have got independent variables and the error term. When we average it, right, average it over time, we'll get rid of time component, right? I have told you previously also, if you have data for time t1, t2, t3 up to t7, you average it, you get only one value, right? And that doesn't have time, right? So yt minus 1, yt minus 2, it could be 1 to minus 7, because they've got 7 data points for 7 time periods. If you average, take the average, you will have only one data, right? Y bar, which denotes the average, and it doesn't have t component. It only has the cross section component I. So we have averaged it out over time. Now we subtract. Okay, now we subtract these two equations. So the first equation, and the second one, which is the average of the first equation. Okay, remember the difference. The difference is that here we have only cross section, because it's averaged over time. So I've got rid of the time component, and here it has pure panel data. Okay, so when you take the difference of that, you will get certain kind of equation which is used for fixed effect estimation. Okay, the interesting thing is that, when you take the difference, the unobserved effect alpha I will get cancelled, right? When you take the difference, it is going to be 0. Alpha I minus alpha I is 0, of course. So that is totally out of the equations. Now the estimation will be uh, possible. So we're getting rid of by eliminating the alpha I in this case. And the LH side is known as the time demean Y. Okay, so these are technical terms that you need to remember. Time demean is nothing but getting rid of time. So technically we call it as time demeaned. Similarly, we're also getting rid of time demean, or we are having time demean X values, independent variables, as well as the error term. Now let's apply this concept to our case study, right? That one that we have taken. Now on the time demeaned data, we can actually use the OLS regression. Okay, why? Because when you have time demeaned data, your errors will not be correlated over time, because you have only cross section error I, j, k, and so on. So you don't have error like uit, ui jt, and then uit minus 1, ujt minus 1. So we expect these to be correlated because there is a time component over time, right? Like the salary of the same person over time. Okay, salary of the person 1. Okay, person 1 for time 1, and salary of the same person in time 2 will most likely to be correlated. Now since we have got rid of the time component, that thing is not going to be there. So errors are not going to be correlated over in this particular case. So we can use OLS now. So by doing this transformation and using OLS, we are estimating the equations. And this is all theory, right? So just for your understanding how fixed effect estimation is done, this is a broad overview of fixed effect estimation. I recommend you to study more about it, to understand more about it, how it is different from the ordinary least square estimation, how the transformation is actually helping us using ordinary least square estimation while doing the fixed effect estimation model. So let's use it for our data set. Syntax remains same that we have been using so far. The model type is now within. Now the fixed effect is also known as within effect. Okay, so fixed effect is same as within effect. Okay, so let's not get confused in this case. Let's look at the results. Now in the results we can see that there are two important variables which are significant. One is experience, the other one is projects. As expected, right? These two are very important variables for somebody's salary, right? So they're coming out to be significant. What about the R square? Now the R square is 0.65. Adjusted R square is 0.56. Now that is significantly higher than the R squares that we have seen in the previous three models, right? Why it is so? Because now we are using the correct methodology, right? So if you use the right estimation technique, the right model for the data, will have a better R square, a better fit rather. Okay, so this is a better fit to the data. Previously we were using wrong models for panel data. So we weren't using panel data model. So this is the panel data model, and that's why we have got the better result. The reason, I mean, if when you are doing in practice, you need not have to try, all three types of estimation that I showed you in the beginning. The reason I showed you is to give, give a comparison study, a comparison study as to how OLS is different from the panel data analysis, and how we can actually empirically show that the panel data models are better fit to the panel data than the OLS models. So how do we interpret? Now education is dropped. That is fine, because education doesn't change over time. When we have taken the average, of course it is not going to be there, because education doesn't change over time for a particular portion, most likely. So it gets dropped. Experience has a positive effect on log salary, and the R square value is pretty good. So that shows that it's a good model. The next one and the last estimation technique that we will be using, which is always compared with the fixed effect model, is the random effect estimation. And in panel data analysis, you will always be trying either fixed data estimation, fixed effect estimation, or random effect estimation. Now, the fundamental difference between the fixed effect estimation and random effect estimation is that it assumes that the individual specific effects, the unobserved effects, I'm talking about the alpha i's, are independent of the regressor. Okay, or the correlation between alpha I and xi is 0. In fixed effect, we had non-zero value. In random effect, it is 0. So that's the fundamental difference between a random effect estimation and the fixed effect estimation. Okay. Other than that, there are other fundamental differences as well. Especially doing the inference, whether it's doing the inference for population statistics. And there will be several questions related to when to use random effect and when to use fixed effect, and it's an important one. And in the last part of this presentation, I'll talk about how to decide which one is better, right? Fundamentally, we know the assumptions are different, but how do we know that there exists correlation between the alpha I and xi? Do we have to do it first before deciding on which one is to be used? We'll see that. So let's use this first. We use the the statement model equal to random in this case. The rest of the syntax remains same. And where we're getting here is that experience is significant, education is also significant, but the R square value is going down. Yeah, it's 42% now. So previously we used to have 65%, it has gone down. But just by looking at the R square, we cannot say that which one is the best model, because best model for this particular data, we have to verify it statistically. So now we have come down to two models. One is fixed effect model and the one is random effect model, and we'll see which one is most suitable for our data, which one fits our data the best. Okay, for that we'll do the LM test. So LM test is used to decide whether you should your data fits random effects versus the OLS. Okay, you might wonder that we are confused about random effect and fixed effect, where we testing with respect to OLS. We'll see that. Okay, so let's just bear with a few more slides. We'll have everything in place. So listen to me just few more minutes and everything will be clear. So the LM is used to decide between random effect regression and a simple ordinary least square regression. Okay, and we'll be using the PLM test function in order to do that. The null hypothesis is that there is no significant difference across the cross-section unit. Okay, so that's the null hypothesis, which implies that the random effect model is inappropriate. So if we are in favor of null hypothesis, then random effect is inappropriate. if we're not in favor of null hypothesis, we're in favor of alternative hypothesis, then we will see that random effect is appropriate. Okay. When we do this, so pool is the result that we have used previously, right? So we just use that, and we're using the function PLM test. So what we're getting here is that the p-value is significant. What does that mean? So that means that the null hypothesis is not in favor of the OLS. So what we can infer from this is that given the fact that the p-value is less than 0.05, that means it gives us some kind of a significance. So null hypothesis, the importance of null hypothesis, gives us the confidence that random effect model is better against OLS. Okay, so we'll go ahead with random effect model instead of OLS. Okay, so just look at the p-value. If it is less than 0.05, then go for random effects. That's the rule of thumb. Similarly, we can do the LM test to choose between the fixed effect model and the OLS. So previously we did a comparison. We did a test to see if fixed random effect is better than OLS. We'll see that for fixed effect as well. Okay, so when we do that, the p-value is less than 0.05, is significant. So we assure that the fixed effect model is performing better than the OLS. Okay, now the question is, we have found that random effect is also better than OLS. Now, how do we decide between fixed effect and random effect? Now, we know that these two tests are better than OLS. Now we have to select one of them. So we use the Hausman test to select between fixed effect and random effects. Now this is done using PH test, a panel Hausman test function. So you have both the components random and fixed, and we use the PH test function to do that. P is significant again, right? P is less than 0.05. Alright, so what it says is that as the null is rejected, the fixed effect method is chosen to model the data instead of the random effect model. Okay, now fixed effect is chosen. Now if p value would have been greater than 0.05, okay, then we would have gone for random effect. But since p is less than 0.05, we are going for fixed effect. Now that's one thing, that's one rule of thumb that one has to remember all the times while using panel data models. We've also seen empirically that the R-square value for fixed effect is the highest, right? It's 0.65 as compared to 0.42 for random effect. So that also had given us an some kind of an indication, but it's always good to do a statistical test in order to find the best fit model. So I'll conclude the panel data analysis like this. I've already talked a lot about this. Just to summarize, panel data modeling is a method to estimate data which is both time series and cross-sectional. I've talked many times. Just remember, it has both time series and cross-sectional component. It is crucial to study the same cross-sectional unit form. It could be firm, it could be country, it could be an individual, an industry over a period of time. Now, that feature is only available with panel data, not with time series data, not with cross-section data. So how your cross sections like firm, like country, like an individual, industry is changing over time is something that can only be studied using panel data analysis. And the last thing, or the important thing, is it accounts for the individual specific heterogeneity, something that is not a feature of cross section, right? It is not a feature of cross section, whereas it is a feature of panel data analysis. So if some of your variables are missing from a cross section analysis, we come across a case known as the omitted variable bias. Omitted variable bias, right? Whereas in panel data analysis, this is part of the analysis. So individual specific heterogeneity across time is something that is there in the analysis. So where are the applications of panel data analysis? We'll find application of panel data analysis in most of the social science, social science and business research. It could be educational research wherein we are trying to find out the performance of students across schools, for different years. Clinical research, for clinical trials and so on. For a given drugs over a period of time. It could be biological research and so on. Financial research, performance of stocks, different stocks for different period of times. So you have different types of stock, different companies. At the same time, you have got data for different years. It could be different companies and their different financial ratios, financial performance indicators, and so on for different periods. And this is very important. In financial research, you have got data for quarterly, or got data for annually, semi-annually, and so on. So it's very important analysis in financial research. Health research, right? The health status of individuals or populations, that also can be done using panel data analysis. I hope you have enjoyed this video. If you have enjoyed, please share with your friends. Please let us know how you found this video in the comment section. Thank you so much. Please subscribe to our channel if you haven't subscribed yet. And please also visit our website in the description section. Please also support us on Patreon. You can go to the homepage of our website. You can also get the link to the Patreon in the description section. So thank you so much.